Today, we're going to use Hartree-Fock theory to study hydrogen molecule, which is perhaps one of the most simplest molecule in chemistry. This molecule has 2 electrons and 2 nuclei. So you have one hydrogen, right? Let's call it HA. This represents one of the protons. And another proton here, HB. And of course, you have 2 electrons. Let's call E1, E2. These are the 2 electrons. And the separation between these 2 electrons is R12, which is, of course, the position vector of R1 minus the position vector of R2. And you can also define the separation between HA and E1 as RA1, and you can have RA2 here. Okay. You can have RB1 and RB2. All right. So RB1 is the separation between HB and the first electron. RB2 is the separation between HB and the second electron. Okay, so we have defined all the variables in hydrogen molecule. Now, let's look at the purely electronic Hamiltonian. We use Born-Oppenheimer approximation to fix the position of protons in the space. And let's just focus on the motion of electrons. So the purely electronic Hamiltonian H is, of course, the kinetic energy of the first electron. I am using the atomic units here. And the kinetic energy of the second electron. And the attraction between electron 1 and proton A. So this is 1 over RA1. This is the interaction between E1 and proton A, which is an attractive potential. And another attractive potential between electron 2 and proton A. So you have RA2. Similarly, you will have the attractive potential between proton B and electron 1, RB1, minus 1 over RB2, which is the attractive potential between proton B and electron 2. Okay, so you have 4 terms for the electron-nuclei interaction. Next, you will have another very important term, which is the repulsion between electron 1 and electron 2. And because repulsion is a positive potential, you have plus 1 over R12, in which R12 represent the separation between electron 1 and electron 2. Now, obviously, this equation, this eigenvalue equation, cannot be solved by the separation of variables, because the coordinate of 1 and the coordinate of 2 are intrinsically non-separable. So we have to use approximated method to solve the Schrodinger equation. And based on variational principle, well, in particular, we're using the linear variational principle right here. So we will have the Hartree-Fock theory. Now, let's consider restricted Hartree-Fock theory. Restricted Hartree-Fock theory provides a variational solution to the original eigenvalue problem. So let's consider minimal basis, right? If we want to do a Hartree-Fock calculation, the first thing is to choose a set of bases. So let's just consider the minimal basis here. Which means let's just put one basis function on proton A and another one on proton B. So the basis function is denoted as chi. Chi1 is the basis function on HA. Let's use the 1s orbital of hydrogen A as the basis. And chi2 is the basis function on proton B. Let's use the 1s orbital of hydrogen as the basis function here. Now, you can just use the original solution to the hydrogen atom, which means the 1s orbital is exponential negative r, right? So this is essentially the solution to the exact hydrogen atom. You can use this orbital as your basis, that's fine. But we can also use a linear combination of Gaussian functions to represent your atomic orbital. For instance, we can choose the 1s here as the STO3G, which means we use 3 Gaussian functions to represent a Slater-type orbital. Well, the exact solution of the 1s hydrogen orbital is indeed Slater-type orbital, right? It's Slater-type. So in this case, we introduce a linear combination of Gaussian functions to represent the 1s orbital. The advantage is that because when you do the molecular integrals, Gaussian functions are more easier to work with than the Slater-type orbital, right? Okay. So essentially, STO3G is, again, what we do here is we are using the 3 Gaussian function to approximate the Slater-type orbital, right? The exact solution is Slater-type, but we're using the Gaussian function to approximate the Slater-type orbital because of the mathematical convenience. Okay. Now, of course, we can also pre-optimize the exponent, right? So usually in the actual molecular quantum mechanical calculation, the STO3G exponent for hydrogen is about 1.24. Okay, that means the real atomic orbital in a hydrogen molecule is smaller than the hydrogen atom. Okay. All right, so this is the basic function. That is our first step. Okay. And because we're doing hydrogen atom and hydrogen molecule, this problem is actually pretty simple because there are only 2 possible ways to combine our minimal basis function. Right? Due to symmetry, you only have two possible combinations. either chi1 plus chi2 or chi1 minus chi2, right? So why is that? Because the first combination gives you a symmetric wave function. This gives you a symmetric wave function with respect to the center of the hydrogen molecule, right? And the second combination gives you asymmetric wave function with respect to the center of the molecule, right? Because this problem is intrinsically symmetric. So you only have two ways to construct your wave function. Okay. So the linear combination we have here in the Hartree-Fock theory are really the molecular orbitals, right? So the first, let's write down the molecular orbitals. The first molecular orbital is denoted as psi 1. Here, 1 means the first molecular orbital. And this is 1 over 2 times 1 plus S12 square root chi1, which is the atomic orbital on hydrogen A, plus chi2, which is the atomic orbital on hydrogen B. So here you will have a coefficient, right? Because psi 1 is normalized, right? And based on this fact, you should have this coefficient. And here, the S12 is just the overlap integral, which is defined as the integral of chi1 for electron 1 or 2. So here we just simply denote the index of electron as I, and chi2 for the same electron. Okay? So this overlap integral, S12, is, of course, a single electron integral. You are integrating over Ri, right? I could be the first electron. It can also be the second electron. So S12 is actually a function of the separation between the two nuclei, right? So if you separate these two nuclei to an infinitely large distance, right? So essentially this is the so-called dissociation limit, then the overlap between the two atomic orbital basic functions is 0, right? Okay. So this is your first molecular orbital. The second molecular orbital is, again, you will have a coefficient in front of the linear combination. This is 2 times 1 minus S12 square root times chi1 minus chi2. Okay. So essentially, you know the atomic orbital coefficient, right? So as we said here, so as we mentioned in the previous lectures, we know that here the coefficient is, the ratio of the coefficient is 1 to 1, right? Here the ratio is 1 to -1, right? So essentially, based on the symmetry of hydrogen molecule, we can directly determine the coefficient in front of the atomic orbitals. This is generally not doable for a polyatomic molecule without any specific symmetries, right? So for that case, for a general molecule, you have to go through the self-consistent field in order to determine the coefficient in front of the atomic orbitals, right? It's just for hydrogen, under minimal basis, you only have two ways to get the molecular orbital based on symmetry. And that's why we can directly get the coefficient in front of the atomic orbitals. Okay. Now, we have the atomic orbitals then we can have the atomic orbital coefficient matrix, right? The C matrix, the coefficient matrix. Two times 1 plus S12 squared minus 1 over 2, right? Because it's 1 over square root, okay? 2 times 1 plus S12 minus 1 over 2. 2 times 1 minus S12 minus 1 over 2 minus 2, 1 minus S12 minus 1 over 2. Right? Because we only have two basis functions, so the coefficient matrix is going to be 2 by 2. So here, the first column represent the atomic orbital coefficient for molecular orbital 1, for psi 1, right? And the second column represent the atomic orbital coefficient in molecular orbital 2, that is psi 2, right? Notice that for the first molecular orbital, the ratio of these two AOs is 1 to 1. And for the second molecular orbital, the ratio is 1 to negative 1. Okay. So again, for a general polyatomic molecule without any specific symmetry, you have to guess this C matrix first and go through the self-consistent field cycle. And then you can get a converged solution of this C matrix, which determines the molecular orbital. Okay. All right. So let me just write down what I just said here. So for minimal basis, hydrogen, we don't need to guess a coefficient matrix, right? Because due to symmetry, we know those coefficients. But for a polyatomic molecule, in general, we have to guess C first and solve for C self-consistently. Right? This is the SCF calculation. Right? How to generate such a guess? Well, you can use, for instance, the Hilcoff theory, or you can just use a null matrix or identity matrix, or you can first look at your molecule. If it does have certain type of symmetry, then perhaps you can fix the ratio of several atomic orbitals, right? So, okay. Now let's review what we have discussed in the previous lecture. So in order to solve this restricted Hartree-Fock equation, right, we have the Rolfing equation. You have the core Hamiltonian matrix, right? the core Hamiltonian matrix element are one electron integrals, right? And this is essentially like you do not have the interaction between the electrons, as if the system, as if the electrons are purely independent, right? And that gives you the definition of the core Hamiltonian matrix element. H12 core is defined as chi1. This is, again, chi1 means the first atomic orbital on hydrogen A for electron I, the single electron Hamiltonian operator, chi2 I, right? So again, this integral means you integrate over the i's electron, and therefore the value of H12 only depend on a separation. Okay, and Hi is the single electron Hamiltonian. So you only have one electron here, electron I, this is the kinetic energy, and you have the one electron interaction potential, right? Which means you have essentially ZA over RAI sigma A, right? So this is the attraction between the nuclei and this single electron, right? Suppose you have 5 nuclei in your system, then you have 5 terms in this summation, right? And of course, the attraction depends on the nuclear charge, right? Capital ZA is the nuclear charge of the nucleus A, right? And RAI here is the separation between this electron I and the nucleus A. Okay. So for our problem, it's very easy, right? You only have 2 protons. So you will have minus 1 over RAI. That's it. Okay. And as you can see, this is truly one electron operator because it does not involve the interaction between 2 electrons. So this is purely one electron, as if there are no other electrons in your system, right? Okay. Now, let's write down our Rothanian equation. You have the Fock matrix times the atomic orbital coefficient matrix is equal to the overlap matrix times the atomic orbital coefficient matrix times the orbital energy matrix, right? So the Fock matrix is a 2x2 matrix, right? Because we only have 2 basis functions, right? And the Fock matrix is the core Hamiltonian matrix plus the effective potential in Hartree-Fock theory, right? This effective potential includes the Coulomb operator and the exchange operator. And you can also define the matrix element by using these 2 operators, right? And this gives you an effective single particle Hartree-Fock potential. All the electrons are, if you look at one single electron, this one single electron is moving under an averaged effective Hartree-Fock potential. And this averaged effective Hartree-Fock potential is generated by all the other electrons. Okay. Similarly, this C is also 2x2. And of course, S is 2x2. And epsilon here is 2x2 and diagonal. Right? because we're talking about the canonical form of the restricted Hartree-Fock equation. And therefore, the epsilon matrix is indeed a diagonal matrix. Okay. And we know the Fock matrix, right? Because we know the core Hamiltonian matrix, and we know the Coulomb and exchange operator, and therefore we can construct the effective potential matrix. And we know the C matrix. Well, this is because of the symmetry of the hydrogen molecule. And we, of course, know the overlap integrals, which means we can construct the overlap matrix. And we know C, okay? So the only thing we don't know and we need to solve for is the epsilon, the Hartree-Fock optical energy, right? So since this epsilon matrix is 2 by 2 diagonal, this matrix form FC is equal to SC epsilon can be also written as two matrix equations. FC1 is equal to epsilon 1 SC1. FC2 is equal to epsilon 2 SC2. Now, when you have a line here, so for those symbols, those are all matrix, right? But epsilon 1 here is a number. Epsilon 2 here is also a number, okay? This is the conventional notation we use, okay? Well, because epsilon is 2 by 2, right? And it's diagonal. So on the diagonal element, you have epsilon 1, which is the molecular orbital energy for the first molecular orbital. And another diagonal element is epsilon 2, right? Which is, again, let's look at it here. This epsilon is epsilon 1, epsilon 2, 0, 0, right? This is the diagonal element. This is the diagonal matrix. So epsilon 1 is the molecular orbital energy for the first molecular orbital. Epsilon 2 is the molecular orbital energy for the second molecular orbital. And on the off diagonal element, those are all 0. Okay. So of course, you can rewrite this equation, which is the Rolfan equation, to two equations, right? C1 is the AO coefficient matrix for the first molecular orbital. C2 is the AO coefficient matrix for the second molecular orbital, right? So they're all, so here, what is C1? C1 is just this part. This is the C1 column vector, which is, of course, a submatrix of the matrix C. What is C2? C2 is this second column, which again is a submatrix of the matrix C. Okay. So C1 and C2 are both column vectors or submatrix of the overall C matrix. Okay. So this is the first equation is for the first molecular orbital, and the second equation is for the second molecular orbital. And the whole equation is written based on atomic orbital basis. Okay. So I think I need to write a remark here. So under the atomic orbital basis, right, we choose atomic basis here. Let's say chi mu. Okay, chi is notation for atomic basis. Mu is the index for the atomic orbital basis. F is not diagonal. Right, that's for sure, right? This is Rolfan equation. We're trying to solve for the orbital energies. The Fock matrix is not diagonal under the AO basis. However, there is actually another way to do the calculation. if you choose the MO basis, that is, if you choose psi A as your basis function, which of course is unknown, this is to be solved, then F is indeed diagonal. Right? Because you have already solved the Rosen equation in order to get the molecular orbital basis, right? Why is that? Well, if you look at the Fock matrix, then if you look at the Fock operator for electron I, and you do Fi psi AI, right? And this will give you epsilon A psi AI, right? This is the basic Hartree-Fock equation. This is the canonical form of the Hartree-Fock equation. And that means if you consider the matrix element FAB, notice that here I'm using AB as my index. That means I am considering the molecular orbital basis, okay? So if you use molecular orbital basis to calculate your Fock matrix, which means you're doing psi A, I, Fock operator, psi B, I, this is equal to epsilon A times delta AB, right? Because this part, Fi times psi Bi is epsilon B psi Bi. Or if you look at this part, psi AI Fi is epsilon A psi A, right? Rigorously, it's epsilon A complex conjugate, but this is a real number, right? Since we're using real functions here. So epsilon A complex conjugate is just equal to epsilon A. And therefore, if you just look at this left part, this is the Hartree-Fock equation, which is the eigenvalue problem, right? So you will have epsilon A times the inner product between psi A and psi B, which give you a delta AB, right? And obviously, if A is not equal to B, which means if you're considering two different molecular orbital bases, then the matrix element of the Fock matrix is equal to 0. And therefore, the Fock matrix is a diagonal matrix if you use molecular orbital bases. Okay. So this is just about the structure of the Fock matrix. If you use different bases, the elements will be different. Okay, the structure of the Fock matrix will be different. Okay. And then we can solve for epsilon 1, epsilon 2, right? We can solve for epsilon 1 and epsilon 2, which are the molecular orbital energy for the first molecular orbital and the second molecular orbital. And here I just directly write down the MO energies for hydrogen molecule under the minimal basis here. Epsilon 1 is equal to F11 plus F12 over 1 plus S12. Epsilon 2, which is the molecular orbital energy for the second molecular orbital, is equal to F11 minus F12 over 1 minus S12. So S12 is the overlap integral, right? And F11, F12 are just the matrix element in the Fock matrix. And those two are actually very easy to solve if you actually try to solve this, these two equations, okay? Because you know the Fock matrix, you know C1, C2, you know the overlap matrix, and therefore you can solve for epsilon 1 and epsilon 2. Okay. And for this very, very simple problem, right, this hydrogen under minimal basis, you can do this by hand. But in general, if the problem is larger and more complicated, you have a standard linear algebra procedure to solve for the epsilon. Okay. And therefore, you can get the ground state purely electronic energy. Restricted Hartree-Fock theory energy for a hydrogen molecule. Again, this is not equal to epsilon 1 plus epsilon 2, right? Because you have double counting in this exchange and Coulomb repulsion, right? So E0 is just, I will just write E0 in terms of the matrix element. And this is equal to F11 plus H11 core plus F12 plus H12 core over 1 plus S12. Okay, this is also easily derivable from the epsilon 1 and epsilon 2. So I will leave this part in your homework. Okay, and the ground state energy. Right, which include the purely electronic part and the repulsion between proton A and proton B, 1 over capital R A B. Capital R A B is the separation between proton A and proton B. And because this is repulsion, you will have plus 1 over capital R A B in the atomic unit. So that's it. So we have solved the energy for the hydrogen molecule under minimal basis by using the restricted Hartree-Fock theory. Now, the Fock matrix element depend on the separation. The overlap depend on the separation. And therefore, the total energy depend on the separation. And this will give you, if you plot the total energy with respect to the separation between two protons, then this gives you the potential energy surface or potential energy curve. Well, for hydrogen, it's really a potential energy curve. But for polyatomic molecule with more than 2 atoms, then it's actually a multi-dimensional surface, and this is potential energy surface. Okay. And if you plug in the value of the integrals, remember you have many integrals. So if you plug in the value of the integrals and you plot E versus the separation, you will solve for the equilibrium distance, which is the equilibrium bond length for the hydrogen molecule. And this is going to be 0.73 angstrom. So you will have energy versus the separation, right? So you will have something like this. So here, the bottom of this potential energy curve corresponds to the equilibrium bond length of hydrogen given by this minimal basis restricted Hartree-Fock theory. And if you do the numerical calculation, plug in all the integrals at different separation, you will get this equilibrium bond length is equal to 0.73 angstrom. And experimentally, this is measured to be 0.74 angstrom. Okay, so without using any experimental measurement, without knowing anything about the experiment, just from quantum mechanics, you can actually calculate the bond length. In general, you can actually calculate the geometry of a polyatomic molecule. Right? This is the prediction by quantum mechanics. Sometimes people call this first principle calculation. That means you're doing the calculation without any knowledge of the experimental result. You're purely doing it by using quantum mechanics. Okay. So, well, now we know the energy of the hydrogen molecule at the equilibrium geometry, which is the bottom of this point, the bottom of this potential energy surface. Now, another very interesting property that we care about is essentially the bond energy. Let's consider dE. Here, capital D means the dissociation energy or the bond energy. E means you start from the equilibrium point. You start from here. And you simply look at the infinity, what is the energy here, right? And then you do the difference. This is dE, and this is your equilibrium bond dissociation energy. So obviously, if you dissociate two hydrogen, if you dissociate a hydrogen molecule, you will have two hydrogen atoms, right? That's your dissociation product at the ground state. Okay. So one way to calculate the bond dissociation energy is to simply calculate the energy of the hydrogen. So at the dissociation limit, you have two hydrogen. So this is 2 times the energy of one hydrogen atom with your atomic basis minus the energy of hydrogen at the equilibrium geometry with your chosen atomic basis, right? Remember, we have to use the same basis here. The same basis function. In a calculation, you have to use the same basis function for describing the species. So essentially, you have 3 independent quantum mechanical calculations. The first quantum mechanical calculation is to calculate the energy, the total energy of hydrogen molecule at the equilibrium distance. The second calculation is to calculate the total energy of an isolated hydrogen atom. The third calculation is to calculate the total energy of another isolated hydrogen atom, right? So this hydrogen atom is really isolated, right? Suppose you only have one hydrogen atom, then you solve the Schrödinger equation. What do you get, right? Of course, for hydrogen atom, we know its ground state energy is negative 13.6 electron volt. This is the exact answer. But here, since we need to use the same basis function, right? For the exact answer, you have the exact orbital. But here we're using the STO3G, which is our chosen basis function. You have to evaluate the expectation value of the hydrogen atom under your basis. And by doing this, the dissociation energy is calculated to be 4.99 electron volt. This is the bond energy for hydrogen molecule. And experimentally, if you measure the equilibrium dissociation energy, which is actually the enthalpy minus the 0-point vibration energy contribution. You will get 4.75 electron volt. Okay, so in the experiment, what you measured is actually not dE. What you measured is, because in the experiment, in reality, the lowest energy level you can get is this 0-point energy level, right? Because you have vibration, and the lowest energy you can get is when the quantum number, the vibrational quantum number, is equal to 0, which is 1/2 h bar omega. So this is the 0-point energy level. So really, what you can get is this part. This part is called D0. This is the so-called 0-point energy included dissociation energy, or bound dissociation energy. And in order to compare D0 with dE, you have to minus the 0-point energy. You need to subtract the 0-point energy from dE in order to get D0. Okay. So let's just compare dE, okay? So by this calculation, we know the dissociation energy is 4.99 eV. And based on the experimental information, the dissociation energy is 4.75 electron volt. I will say this is a pretty good result in terms of the molecular quantum mechanical calculation for such a small basis. Of course, you have some error about 0.25 electron volt, but you're using a very small basis, and this is actually a very approximated calculation. And this is already a good result for this level of theory. Okay, so let's dig into the details to see what actually happened. So we're using the STO3G basis. Right? This is our chosen basis function. So the STO3G basis energy of the hydrogen molecule, by using the restricted Hartree-Fock theory at the equilibrium distance, is equal to negative 1.1167 atomic unit. Okay, basically this is the number you will get if you plug in all the values of the integrals. Okay, and the STO3G hydrogen atom, right? You have two hydrogen atoms actually, so this is going to be 2 times negative 0.4666, and this is negative 0.9332 atomic unit. Here, because we have to use the same basis, so the energy of an isolated hydrogen atom is calculated as the expectation value of the STO3G basis function H STO3G. The STO3G is just an approximated basis function we use. It's not entirely equivalent to the exact solution to the hydrogen atom Schrodinger equation, right? So as you can see, for an isolated hydrogen atom, the STO3G energy is negative 0.4666 atomic unit. And based on this, we calculate the dissociation energy, right? The energy difference between these two is the dissociation energy, which is 4.99 electron volt. Okay, let's compare this result to the exact answer. Now, for hydrogen atom, of course, we know the exact answer. If you consider the exact answer of 2 hydrogen atom, this will be equal to 2 times what is the exact answer for the ground state's hydrogen atom? Well, that is exactly 0.5, negative 0.5 atomic unit, which is equal to negative 1 atomic unit, right? This negative 0.5 is the exact eigenvalue of the hydrogen atom Schrodinger equation. All right. So you know when you use an approximated basis STO3G, you will get a higher energy. Well, that's actually what we expect, right? Because based on variational principle, your energy, your approximated energy will be higher, not lower than the exact answer, right? Okay, so that's not surprising. Okay, let's look at the exact answer for the hydrogen molecule at the equilibrium distance. And this is actually negative 1.1746 atomic unit. Okay, so you ask, how do you know the exact answer for the hydrogen molecule at equilibrium distance? The Schrodinger equation is not separable. You're right. So there are two ways to know the exact energy for the hydrogen molecule. One way is to use the information from experiment. If you assume the experiment has no error. For hydrogen molecule, actually, the experimental value is highly reliable, okay? And then you can estimate the exact answer for the hydrogen molecule at the equilibrium distance as basically 2 times the exact answer of the hydrogen atom, which we know quantum mechanically, negative 0.5 atomic unit, minus the experimental dissociation energy for a hydrogen molecule. Of course, you need to convert that experimental value 4.75 eV to atomic unit, okay? Because the energy of the exact hydrogen solution is negative 0.5 atomic unit, okay? And then you will get negative 1.1746 atomic unit, okay? This is one way to get the exact answer for the hydrogen molecule. But you will say this is not first principle because you use knowledge from the experiment. You're right. So a truly first principle way to get the exact energy of the hydrogen molecule at the equilibrium distance is first you do Hartree-Fock calculation, then you include all the possible configurations that can be generated by the Hartree-Fock ground state Slater determinant. This is the so-called configuration interaction. And then use a complete basis set. So you use essentially an infinitely large basis set, which can be done actually by extrapolation. So you use a medium size, a larger, and even larger basis set. And then based on this 3 point, you can extrapolate to the complete basis set limit. So this is the so-called full configuration interaction with the complete basis set approach. Sometimes people call that complete configuration interaction. Okay, by using this, we can get the exact answer. Of course, this kind of calculation, the full configuration interaction with the complete basis set, is extremely expensive. And we can only do it for small molecules. But again, it is in principle doable, and it is entirely first principle, entirely quantum mechanical. And you will get the answer. Okay. Anyway, now we know the exact answer for the hydrogen molecule at the equilibrium distance, which is again lower than the STO3G solution, right? Which is lower than the Hartree-Fock solution, which is essentially a linear variational calculation. Okay. So the exact answer for the dissociation energy would be here. Now let's look at the error. If you compare the STO3G hydrogen atom with the exact hydrogen atom, which means you're comparing these two, you will have an error about 0.0668 atomic unit. This is the error. Your calculation, the energy of your calculation is too high as compared to the exact answer. And your calculation is higher than the exact answer by positive 0.0668 atomic unit. Okay, this is for hydrogen atom. Let's look at hydrogen molecule. Again, your approximated calculation is too high, and the error is positive 0.0579 atomic unit. Right? So you see, the reason that you get a good overall answer for your calculation is because, well, the errors are similar to each other, right? This is because you use the same basis. If you use the same basis consistently for calculating the same quantity, essentially you will have this sort of error cancellation, right? For hydrogen, you overestimate the exact energy by about 0.06 atomic unit, right? For hydrogen molecule, your calculation overestimate the exact energy by about 0.0579 atomic unit. And therefore, they cancel out when you do the difference between the hydrogen atom and the hydrogen molecule. And this is why it is extremely important to use the same level of theory, same quantum mechanical calculation, with the same basis set. Okay.